Hello, everybody. I am Pilar Rodríguez Márquez. I am a student from Benemérita Universidad Autónoma de Puebla. I am incorporated to Facultad de Ingeniería Química. It's located in Puebla, Mexico. And I'm going to present my work, The Use of Clay-Based Materials as Low-Cost Substrates for Commercial Photocatalysis. The authors are Pilar Rodríguez Márquez, María Pedraza Chan, and Alejandro Escobedo Morales. Well, let's start with the important. As we know, water pollution is a global problem that requires alternative strategies for its solution. Photocatalytic treatments have proven to be effective, but several issues concerning application of powder materials must be solved. This work focuses on the fabrication of immobilized zinc oxide photocatalysis using clay as low-cost raw material. The results show that the obtained supported materials present photocatalytic activity in the degradation of rhodamine B dye. In addition, the estimated EGs of power and supported zinc oxide photocatalysis suggests that the fabrication process does not modify the chemical composition of the activity phase. This is part of my abstract. And why do we choose zinc oxide? It's because it's considered among the best photocatalysts due to its physicochemical characteristics, non-toxicity, high availability, and low cost. However, it is used in powder from present several challenges, driving to use supports to immobilize it. An ideal support must provide strong adhesion with the active phase, high specific surface area, and contaminant absorption capacity. A clay-based support meets these characteristics. Moreover, most of these type of materials are cheap, porous, and has excellent thermal, chemical, and mechanical stability. This work explored the possibility to use ceramic materials to support commercial powder zinc oxide as photocatalysis. Well, in the methodology, the synthesis of materials were using commercial clay, both in San Pablo del Monte, Tlaxcala, Mexico, that was purchased and used as a receipt to fabricate these shapes ceramic supports with a diameter of 2 centimeters, thickness of 3 millimeters, using a STM norm to apply to obtain the appropriate plasticity. The clay pieces were left to dry for 14 days. This was important to get a good consistency. Then a clay slip was prepared by mixing clay, zinc oxide, and binder in a 9-15 two-way ratio. A thin slip layer was applied on the support by immersion technique. The impregnated support was left to dry for 1 day. After, a heat treatment was carried out by applying microwave radiation using a microwave ceramic kiln and a commercial microwave oven. Characterization. The obtained materials were characterized by diffuse reflectance spectroscopy. The EG of materials was estimated using the Kovelka-Munk formulas and the Tog method. Absorption. The conditions where 8 zinc oxide coated supports were immersed in 80 millimeters of a 10 ppm rhodamine B solution. The system was kept at constant temperature, magnetic steering, and airflow. Then, the catalysts were left in contact with the solution during 100 minutes to ensure the absorption equilibrium. The actual concentration of rhodamine B was determined at regular intervals by spectrophotometry. Photocatalysis test. The conditions for the photocatalysis experiment were the same as described above. Additionally, the system was illuminated using a mercury lamp during 100 minutes for the evaluation of powder zinc oxide. The same protocols were used, but a catalysis dosage of 0.5 milligrams. Well, in the results, we can see the synthesis of the materials that were very simple, but we have to learn and manipulate the dosage. And that was the maybe hard part, but all already were made to ensure a good immersion and a good engulf. We have also the obtained for tau plots, and we obtain a 3 0.2 EG's value. Also, as we can see in the results, we have the graphs of spectrums and the coloration of rhodamine B. We can see that the greater reduction in rhodamine B absorption when using a powder photocatalyst compared to a ceramic support can be attributed to a higher surface area of the powder, better dispersion in the solution, and the ability to absorb more light, although each system has its own advantages and disadvantages in terms of handling and overall efficiency. The experiment gave us results like the follows in the table 1. Remotion efficiency and reaction coefficient rate. As can be observed, there is indeed degradation in both photocatalytic process. The supers do show an adequate absorption behavior in the dark phase. However, their degradation process is slower compared to the use of powder, which also has higher absorption. As conclusion, zinc oxide powders were immobilized on low-cost clay-based supers using the proposed methodology. It was determined that the fabrication process did not modify the optical properties of the active phase. The obtained material was used as a photocatalyst to remove rhodamine B dye from water. After 200 minutes. The total removal efficiency of the supported photocatalysis was 23.3%, that is less than its powder counterpart. It is attributed to a lower activity surface area and the absorbed fraction of the incident light, although immobilized photocatalysis offer clear advantages in terms of handling and reuse. Optimization of operational conditions are required to improve their photocatalytic performance. Here are my reference, and I want to thank you to everyone for watching, and thank you to all the people involved in this work that make this possible. Thank you. See you later.